In Lab 3, we found the magnetic field of bar magnets, which have a permanent dipole. We wanted to measure the distance dependence of the magnetic field due to a bar magnet, which should be approximately 1 over r cubed according to the Biot-Savart law. The Biot-Savart law is an equation that describes a magnetic field created by a current-carrying wire and allows you to calculate its strength at various points. Using it requires calculus, and then you can derive the formula for the magnetic field of the dipole from integrating the original Biot-Savart law. The result indicates how the magnetic field of a dipole, regardless whether it's on axis or not, is still proportional to 1 over r cubed in terms of distance from the dipole to the observation location. This shows the magnetic field will decrease with increasing distance by this factor. Materials needed for this lab were a smartphone, a bar magnet, a meter stick, a ruler, and the Excel spreadsheet provided to us by our professors. On the smartphone, it was required to download a special magnetometer app, such as Teslameter, in order to measure the magnetic field due to the permanent dipole magnet. The Compass app that comes in the smartphone is not sufficient because Compass applications usually use GPS tracking to calculate the geographical north instead of the magnetic north. They also sometimes filter out local magnetic fields, which would be an issue since we're trying to measure the local magnetic field of the magnet. To find the magnetometer chip in your phone, you had to slide the phone slowly along a line perpendicular and then parallel to the meter stick, putting tape where each one is where the y is at a minimum and the x is at a maximum, or vice versa. At the place where the two tapes intersect is the square where the magnetometer is located approximately. In the Excel sheet, we measured the distance where the x component of a magnetic field is 1,000 microteslas, and then made magnetic field measurements there, and also at 1.5 times that distance, 1.75 times that distance, and then 2 times that distance. We then plotted ln b and ln r to get a graph where the slope is n and the intercept is ln k, since the magnetic field b equals kr raised to the n. The experimental n value, which was the slope, was negative 2.5. The n value that should have been recorded was negative 3 due to the Biot-Savart law. We then used a computer model to visualize the off-axis magnetic field. The expression shown here is very accurate at far distances from the dipole, but less accurate up close. The computer model can help us visualize this expression. We're also able to solve for mu and plug that into our computer model. We could also compare the values calculated by the computer model to the value calculated by the phone app, which was done when the magnet was tilted at a 45-degree angle. The computed value and measured values are listed below. Some additional questions. If I had not oriented my experiment to compensate for magnetic north, the results would have changed by being skewed, since the Earth's magnetic field would have not been canceled out and been ignored, so the magnetometer would reflect that as well as the bar magnet's magnetic field, causing it to be much larger. If I were to stick two identical magnets end to end together and then run the experiment again, the measurements would differ by having a stronger magnetic field being calculated, although it would not be twice as strong since one of the magnets would be an entire magnet length further away from the magnetometer than the first magnet. So you would not be adding the exact same values on top of each other. In conclusion, key physics principles demonstrated in this lab are magnetic field, magnetic dipoles, and distance dependence. The results I achieved were close to the actual value of n, but human error could have contributed since the magnetometer app was a little bit hard to use, and also the fact that it is very hard to eliminate all magnetic influences from around the lab site in order to just record the magnetic field of the bar magnet itself.